We now move on to the next presentation from Alessandro Salgarello, Chassis Advanced Engineer at Hyundai METC, and Francesco Notaro from the University of Naples. During their presentation, prepared with Vehicle Dynamics Engineer Florian, they will introduce a new EPS assistance model for virtual vehicle calibration. The model offers improved functionality and realism for calibration engineers and is used to develop the steering feel of new vehicles.
All right, so good afternoon, everybody. Good afternoon as well to whom is following us on live. And yeah, we are thrilled to take you through the development of the steering assist model that we made in HMETC and how we integrate it in the driving in the loop environment. I'm Alessandro, together with me is Francesco from University of Naples. So, just a quick slide about who we are. So, Hyundai Motor Europe Technical Center. We are located in Rüsselsheim, close to Frankfurt Airport, and we are the European R&D for the Hyundai Motor Group. So what we do is that we take the global platform of the Hyundai, Kia, and Genesis brand, and we adapt to the European taste and requirements. We have as well another test center close to the Nordschleife that is mainly used by our high-performance colleagues, which are taking to the road the N cars, so like i30N, i20N, and even more to come. So, I promise this is the last slide about HMETC, and we start with some technical content. So we will go through the motivation and the background of this work, continuing talking about why virtual steering feel is important, and what is our virtual testing environment. Then I will pass the word to Francesco, which will show you how he developed the logic, and how he integrated it in our driver in the loop tool. Finally, he will talk about the subjective evaluation, and we will go to the conclusion. So, the motivation. Well, if you think about the first thing that you do after you switch on the car is putting your hands on the steering wheel and start driving. This is a direct feedback to the driver regarding the vehicle behavior, and it's giving as well the confidence on how the vehicle is driving. And therefore, our target is to give high confidence to the driver so that he feels safe, but as well to give the unique DNA that we decided for our brands. On top of that, we need to be consistent. We cannot give two cars from Hyundai and have completely different steering feel, because then you don't recognize the brand. What we look at is steering effort. The on-center feel, very important for all the precision of the car. As well, we look on the response and the feedback from the road. Why using simulation? Well, I think we are now since 2 days here, and we have heard about front-loading activities regarding tuning of the car, regarding suspension, kinematic, and compliance. Steering feel is definitely influenced by that, and therefore is something that is done at the very late stage of the development process. Now, in Hyundai, we are doing already what I said, and we wanted now to front-load as well this activity. The problem is that simulation, not so many people believe in it, and especially on steering feel, this is quite complicated. And therefore, our research question, how we can represent in the virtual environment the steering feel using a model in the loop approach. Now, virtual steering feel. We have many influencing factors in the real world and in the virtual world. We have the road, of course, can be different, smooth, rough, and in the virtual world, we laser scan usually in order to have exact representation of them. Then we have the tire, different dimension, different tire spec on the development process, and usually we have different tire models as well. Suspension, that I said, is already influencing quite massively the steering feel, and for vehicle models like VI, car real time, we have lookup table for the key and C properties. Then we have the steering system, very high stiffness, very low damping, and definitely one of the few components that has always a control, at least here in Europe, which is the EPS. And then regarding the steering model, we have quite complicated model. Usually, it's a multi-degrees of freedom, and the EPS is represented only by the assist curve. Then the prototypes, not always available, at different variants of different stage, and our virtual prototype that instead are always available, But then what is important is to give a realistic scenario and a hardware that can give as well a correct feedback to the driver. And talking about the virtual testing environment, when we do subjective evaluation in HMETC, we use our static driving simulator. The steering feedback loop, we have an hardware and a virtual part. So the hardware is real, and we have the OE steering wheel and column, and we have the feedback torque actuator connected to the lower column connection to give the feedback torque that the driver should experience. On the modeling side, we use the rack pinion steering model, or FEFE model, which is connected to the vehicle dynamics model, and hopefully, and as Francesco will show, the APS logic now. All these models are run in real time using a concurrent IOC. And that's for the moment from myself, so I will give the word to Francesco.
Hello everybody, thank you Alessandro. I'm Francesco, and I will show you my work that I did with HYUNDAI on the EPS logic development. I will start by showing you the requirements and the background I found in HYUNDAI when I started working with them. And so the first thing is that there was a lack of immersion when driving. So that was caused by the artificial representation of the steering wheel that they had before. So we had as a requirement an improvement in the sense, so to have a better immersion, especially for the drivers when they had to do evaluation of each kind of vehicle dynamics maneuvers, both for handling and ride. So what we had before in terms of steering wheel, does it work? Yes. Of EPS modeling, we had basically the native VI implementation, so a simple lookup table for the assist torque of the EPS, and that gave us no possibility to influence the on-center field and the return feedback of the steering wheel. So without changing the mechanical properties of the FEFE model. And so what we wanted to achieve with my work was to have all the most important EPS functions you can find on real cars available in a virtual environment with the possibility to tune them in the virtual environment. So we started from the simple lookup table, a simple assist function, and then we added on top of that other functions. The first one was the damping control function. That is the main way to stabilize the system without changing the damping of the system itself. Yeah, basically it just adds a contribution to the overall damping of the system. And that also gives a better feeling to the driver when it comes to the return, especially at higher vehicle speeds. And, but the downside of having this function is that you have more hysteresis overall in the model. And so for that reason, we have an on-center control function that improves the on-center by aiding the driver in the more dynamic maneuvers and by compensating the EPS motor inertia that is present in the mechanical model and the overall level of friction of the mechanical model. Then we have a very important, as I said before, improves the on-center field. And then we have a very important function, the active return function, that is used for lower vehicle speeds to have the steering wheel return to the starting position. Without that, you can't have that for the lower vehicle speed. And that improves a lot the immersion of the driver because you feel like in a real car when you have this kind of function. And, but the downside of this function is also that it adds hysteresis in the on-center when driving at lower vehicle speeds. Overall, all the functions put together gave us a better representation of the steering field compared to the measurement data, and in respect of what we had before with only the native VI implementation, and as you can see in the graph. And that is due to the fact that we can also have a more realistic mechanical parameterization of the model, and we have a better response in the more dynamic maneuvers thanks to those functions. And as you can see clearly from the graph, there's a very big improvement in the on-center characteristic of the steering field. A big challenge of my work was also the integration in the driver in the loop environment. We have at HMETC. As Alessandro explained before, we have a concurrent machine that runs with classical sim workbench environment. And the standard workflow to implement a Simulink model, because I did all my work in Simulink, is to use the ML toolkit to compile the model. It's very simple. You can generate the source code from your model and then compile the source code into Linux, and then execute the executable that calls the library and have it interact with the VICA real time. But this procedure gives us some problems for all our use cases, because to modify the parameters, so if you have different tuning files, with this workflow, it's difficult to do. You have to change the parameters or manually from the RTDB, or you have to code some scripts in C or in Python to do the parameter change, or you have to compile each time the model with different parameters, and so it's not really feasible to do that. And we had to find other approaches to parameterize the system. So the first one was to include an initialization function into the source code of the model. So we did that by first obtaining with the ML toolkit the model source code. Then we obtained the source code for the initialization function, starting from a MATLAB function through the help of the MATLAB coder. Then we put it all together, compiled the new library with the inclusion of the initialization function. And that library is able to call an ini file that contains all the parameters and all the settings you need to run the model. And there's no need to recompile the model if you want to change some parameters. You just change them into the ini file, or change the ini file, and you can have new parameters. The other alternative is to use the functional mockup interface. So you compile the model as a Linux FMU at the start, but you have to include the source code for the FMU. Then you can use that source code to compile a new FMU into the Linux environment. And that FMU interacts with the FMI master library from VI Grade that is able to access in real time the model description file, where all the parameters are stored for the EPS logic. And so even with this approach, you don't need to recompile each time the FMU if you want to change the parameter. You just change the model description file. So to compare quickly the two environments, to understand which method is better for each use cases, we compare the environments, the final environments that two approach gives us. So the first approach gives us this kind of environment where, as an upside, we have a simple way to change the parameters through the help of the ini file. And also, with this way, we have a real-time access to all the input-output variables and also all the parameters on Sim Workbench with the real-time database. But the problem of this approach is that it's more complex to implement. You need some programming skills to do that. And also, the environment you have is a bit different to the one you have with the offline simulation. With the other approach, the one with the FMI, you have a simpler implementation. You don't need to do much coding to implement the model this way. And also, you have a gray box model at the end that you can share with external partners without problems of IP disclosure. And also, you have the same environment you run offline. You can replicate it one-to-one online. And but the downside is that changing the parameters through the VFM or with the model description is a bit harder compared to the ini file. And also, you don't have the full access of the parameters into the real-time database, because the FMI only talks with the VIK real-time, it's not included into the Sim Workbench environment. So at the end of the process, we did a subjective evaluation of the model with the help of expert test drivers. And as a baseline, we used the standard steering model, and the evaluation was based on the comments, the most popular comments of the drivers. And you can see on screen basically the comments without my EPS logic. And to summarize, the main problems they found was on the on-center field, the returnability, and the lack of road feedback. And with the EPS logic, all those things were clearly improved, and that gave us the feedback that this kind of logic can be used for steering tuning, and also to train the new tuners to do their job, so to learn how to tune this kind of logics. So for the conclusion, I will throw it back to Alessandro. That will conclude the presentation.
Yeah, thanks, Francesco. Very good job. Already told you. I will go quite quickly because we are running out of time. So, steering field with using simulation is not that far away anymore, and we have seen that having the EPS logic is improving massively the driver immersion and the capability of them to evaluate the vehicle dynamics. So, in terms of an application, the enhanced enhancing model with the EPS can be used through the entire development process, as is an open model that we have developed in-house. And it's very nice because we can quickly exchange EPS parameter. Instead, let's say, regarding the implementation, now we have seen two different ways that we can now, let's say, use when we want to exchange models with, for example, suppliers. So we can tell them how exactly we would like to receive the model. And let's say, all the questions that we were asked before, is it good enough, is it complicated? Well, we can say that no, we can use simulation to do steering field development, and from now on, this will be, let's say, our standard environment for offline, but especially for driver-in-the-loop application. And with that, that's the end of the presentation, so thank you very much for your attention, and if you have any question, we are thrilled to answer them. Thank you.